Welcome everyone to the Pandit Madan Mohan Malviya um, National Mission for Training Teachers. And this is day 5, session 2. We finished with the Magma just a few minutes back. Now I'll start on the 5G core. So the topic I plan to cover in the 5G radio and core integration is one, first the data communication fundas, which you need to know. Second, what's the 5G, and so this will cover the entire 5G, not only the new radio, 5G new radio, but also the core and the systems, 5G systems. But the focus here is on the radio mainly because we Magma covered the part of the core. However, the standards was not covered. It was more of a open source there. So that's what I'll cover. And the 5G system is obviously we have to see what are the 5G use cases for the system, for the applications and all those. Third, we'll cover the spectrum and licenses, and with respect to India, a little bit more. Then, what is there in it for me, as usual, for the vendor dilemma, and what is the open source, and what are the benefits to them and to the society in general. Then, what is the 5G new radio, and how does it show up with respect to core and the stack systems? Basically, the standards, what they are there, and then we'll talk against what is standards versus what is deployments and how are Indian contexts established for 5G, and then some aspects of research which I would like to share to encourage and motivate the people who are waiting to find new areas to put research work. And finally, we'll deal with the use cases of 5G. In this, private 5G network is one of them, which I think I'll leave it as a external, like we did for demo of the Magma. That portion I will leave it to our guru, and that is Prem, who is working for Cohere on the 60, and we'll leave him with that. And question and answers we'll take, or we'll do it in the forum. So let's move on to the internal. First is data communication fundamentals. Data communication is key, and what you can uh, see on the right side, the two picture, that's very important. The left side stack is the OSI 7-layer stack. It starts with the physical layer, the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and the application layer. So this stack is a OSI stack. It has been there for pretty much now, starting at least 30, 40 years to what I know from my experience. And also on the TCP/IP stack, the Berkeley TCP/IP is where the uh, most of the people ported from, and that stack deals with the physical layer or anything under the network interface and below, and then it talks about the network and then the network is nothing but the IP layer, and transport the UDP and the TCP layers, which is uh, what you call connectionless and connection oriented, reliable and unreliable, and then comes the application layer. So from the OSI layer point of view, physical layer, data link layer, network layer, these are all covered as instead of 3 by 2 of the stacks in the TCP/IP, and transport layer is at the same layer as transport, and the session presentation and application is folded as part of the application. Now, what I mean by this is you can look at stack in different ways, but we have to start somewhere. And here, in the wired case, we will talk at the physical, as well as wireless, we will talk at the physical. So, what is the difference? So, one has a media which is like a copper, coaxial, or fiber. The other has a air as the media. So, you can use air with a wireless media, wireless radio, or you can do with a wired with copper coaxial fiber. Each one has its own plus minus. Initially, everybody started with the ISDN, and there is the copper, so dial-up access ISDN, and then moved on to coaxial, which is the cable TV and all this, and everybody can use IP now. And the fiber is the one which is photonic and optical communication that has got core, multi-core, and several things, and that's a faster one. Not only that, but that's the one for broad band. In fact, most of the cell towers in the 4G have the backhaul as through uh, fiber, and that's key because that is where your front haul, mid haul, back haul come in these days. After the over the radio access to the cell. So Wi-Fi wireless communication, data communication covers both the fixed network as well as the mobile network and both communication. And so the wireless, when we talk about, we mean the Wi-Fi, we mean cellular, we mean satellite, all over there. Now let's talk about the physical layer. Physical layer, you got the media or the OTA, or over there, what we term. So the line interface, line can be a device to media and vice versa. So it could be downlink, uplink. So if you are dialing, you go and you connect and you start downloading, that is downlink. Uplink is when you connect and you provide your ID, etc., in a access from your home or something, or even from your work. So those are the line interfaces to the device. If you have a network interface card in a server somewhere, then what you connect is to a device, and the media is in that case probably wireline, but it could be even like you have a uh, access point in your home or somewhere, you find the antenna, and then that's a over the air interface. So any line, whether it's a over the air or the line interface, is what matters, and that has a configuration. It can be point to point or point to multi-point. Like example, access point at home may connect to many notebooks or many devices on the Wi-Fi. So that's a point to multi-point. So you can have point to point, or sometimes it is simply one connection from your work or home to the service provider who has got a fixed line, and that could be point to point. So you can have point to point, you can have point to multi-point line configuration. The data, usually data are represented in binary bits as 0 and 1. Voltage wise, they may be different. Some may be minus 12 to plus 5, some could be plus 5 to 0. And that depends on what, whether it's a TTL, CMOS, and different types of semiconductor which are used in the chips. Based on that, gates and all, whatever is derived, they have different binaries. But representation wise, what we are looking is 0 and 1 binary bits. And I said there are also these days requirement for uh, multiple baud rates, like you can have levels, 2 levels, 4 levels, 6 levels, depending on 2 to the power n. So I can have a 4 level, and then that can give me 2 to the power 4, which is 16. So we can have 16. So we can have a qubit with 16, or we can have a baud with 16 with 4 level. So that is where the innovation I'm expecting from people, especially based on the Nyquist level formula, very similar to uh, capacity from with the noise from Shannon. We'll look at it, but at this time, the physical interfaces, you can have transmission mode simplex, half duplex, full duplex. That is one way, two way, with time division, with what do you call? Because you do sequential. Generally, it's not like your parallel bus. Most of them, even PCIs these days, for IO, you use a serial interface. Most of them are serial interfaces. So you have to serialize, deserialize. So all transmission are done as sequence of bits and bytes. So data rate, transmit, receive bits per second is what is important. Topology for a network can be bus, ring, star, mesh, many types of topologies you can use. Ring especially is very popular in the fiber optics because you have to have optical rings all over so that you can cover a greater area with a lesser expense. Plus, you can have redundancy to support ring clockwise, anti-clockwise. So if one fails, you can run the what you call traffic through another. So those kinds of things are there. Then you got the analog versus digital. Analog is becoming again important because of the what you call quantum computing, because you need to deal with the analog at certain point of time. Earlier days, 40 years back, it was all analog, and digital was rare. Now it is coming around. All things go around and come around. Hopefully, analog will become equally mixed signal with becoming more important. So these are the physical layer characteristics which we need to worry about. Then link layer. So link layer, as you see in the second, after physical layer, we describe the link layer. So in the data link layer, what happens? You got to have a address, and that is MAC address usually, 48-bit address, which is assigned uh, by the industry for the Ethernet. Of course, you get that MAC address, and then you can form from that the addresses which is necessary to identify the host or the location of the NIC where it is, and assign the IP at the top on top of it. So payload. So then we have to talk about once you talk about the layer 2, then you have to talk about the frames, not the packets. Frames have the addresses, headers, payload, and CRC to cover up the error correction and all that, so that you don't allow any single bit failures or multiple bit failures depending on what you use your header and payload. So IEEE has got the standard which are featured for wireless very heavily, 802. In fact, 802.3 is the Ethernet most important. And then Wi-Fi, obviously 802.11 A, B, G, C, and all those, and Wi-Fi 6 and Wi-Fi, what do you call it, for 5G, and Wi-Fi 6E for the 6G extended and all that. You can use signaling like TDMA, time division multiplexes, and frequency division multiplexes. Then you have got CDMA, space division, and then you have got OFDMA. So various protocols have been used in 2G, 3G, 4G, 5G, and all that. OFDMA is one which is used in the 5G on the downlink, and then you have to use a single carrier FDMA, CFDMA, which is another one for the uplink. So uplink downlinks are different, and similarly for 6G there is something different which is coming up, and you can look up on that. So LTE, usually we have been doing LTE. 5G is LTE, but 4G is LTE. Sorry, so 4G LTE is a long-term evolution, they call it, and the evolved packet core, that is the core side of it. In the radio side of it, it is LTE, and in the long-term evolution, it has got LTE. So it evolved from actually 3G from the HSPDA, and there are many packet protocols. The LTE advanced, those are the ones which enable us up to 20 megahertz. So the target here was 1 gigabits per second, and usually it starts with 1 meg, 10 meg, 2 meg, and 15 meg, and 20 meg, and so megabits per second. The spectrum, of course, spectrum efficiency decides it, and that depends on the turbo coding and various codings that are adopted to ensure that wireless reliability is high. So therefore, you have to resend and overall, you can get a bandwidth. As I said, if you have a carrier FC and you have a 20 megahertz bit, then you can say FC plus minus 10 megahertz. That's the band in which you operate. And so 5G is instead of 20 megahertz. So LTE is not just 4G is not limited to just 20. I would put it, it can be 1 to, so it's a variable bandwidth is allowed. Variable bandwidth is allowed. 1, 3, 5, 7, 14, some 20, some numbers are there. Similarly, the bandwidth in the 5G is 100 megahertz. So you can have contiguous or non-contiguous. If you are non-contiguous, then you can do a carrier aggregation. That means you can have one in a certain band in gigahertz. Let's say maybe 700 megahertz band. If you have a let's say 20 megahertz available, and then you got in 1800 megahertz another 80 megahertz available, then you can bring these two together and use the two bands together, slap them together as a carrier aggregation, and take the traffic that way. So that way you can do a lot of innovation, 50 plus 50, 20 plus 20 plus 20 plus 25 times types. And 100 megahertz is the minimum for a 5G. You can even go more, 100 to even up to 1 gig. Usually 100 to 600 is more popular, but you don't do it that way, because why would you do that? You can separate and get much better. So 100, 200 is the more likely. Nobody does beyond that. And no reasons at this time, but you will never know. There will always be use cases which will need them. But nevertheless, this is the current state of affairs for And the 6G, which is 6G is in the 6 gigahertz. They are 80 to 160 megahertz bands. They are not 100 actually, but 80 and 160 you can even still do for a home network. 80 gigahertz, why not? It doesn't matter even if it is not 100, but it can give you based on the uh, sparse coding used or whatever the coding they use, they can definitely produce a high bandwidth available for the home users or even for the private CBRS type applications. Uh, we can uh, use that. So cellular, you can see the Wikipedia has got that cellular network detail. You can go over it. So now we begin the journey to the radio core. So we will not go back into 1G, 2G, 3G. We'll start with 4G. 4G is available, and you can. How did 4G grow? The 4G grew because of video traffic. Demand for video traffic was so large that people really latched on to LTE, and then LTE grew like mad over last 5 to 10 years. It has been growing, and it has grown to its limit, and therefore we need better uh, what do you call bandwidth and throughput and response. Even though LTE was a rush for the madness for the high speed, you always see speed testing being done by the providers, but they don't do latency testing. And latency is what is the key for the 5G. And the targets for uplink downlinks, downlink is speed of 20 gigabits per second, and uplink is 10 gigabits. It's half, 50% is uplink. So this is the targeted. Okay, the 5G targets for the downlink is 20 gigabits per second, uplink is 10 gigabits. Latency, it's in the range of 1 to 10 millisecond, and usually user plane ends up with a 10 millisecond. Control plane, some of the things which can be done faster, especially radio interface, radio intelligent controller for near real time and non real time. There you tend to use the control plane, uh, trying to get to near to 1 millisecond. Sorry, 1 millisecond, and then uh, management plane. Obviously, it can afford to be a little bit more. Uh, Relaxed, and you so 1 5 10 types of is what is the targeted. Actually what happens is it is in between 1 and 10. Now devices per square kilometer, 1 million devices need to be deployed to be able to support the 5G. Now this depends also on the whether it's in the rural or it's in the urban, where are you deploying your devices. And so yeah, but more importantly, users should be supportable. That's the key. If you can use 1 million people in a square kilometer, that's an urban place where you can support that. Because uh, in the 4G LTE, we had somewhere 100 to 1,000 users per cell tower types, concurrent, obviously. And when you do statistical multiplexing, it is much more. It is not just 1,000, because you've got 24 hours and everybody doesn't talk 24 hours. It's only peak hour management which is important. It's called bouncing busy hours and all this. So depending on the busy hours, you can spread that. So that's the talk about in the device per square kilometer. 1 million subscriber or devices per square kilometer. Now, power, obviously, power, it comes to saying that there are facts, figures which says that you need around 10 to 11 kilowatt of power on a base station for 5G. Uh, so that's still a very high figure, and we need to bring it down. So, example, if you have an antenna, you do a 60 watts or 70 watts antenna, multiple MIMOs. So you got 64 MIMO, 4 by 4 MIMO, 2 by 2 MIMO. MIMO is multi-input, multi-output. So single user MIMO, multi-user MIMO, those are the terms used usually for the antennas. And when we have got radio units or radio remote units, antennas, then you need to make sure that the beam formation, which provides the coverage, is sufficient. And to bring a coverage, either you do a narrow beam striking directly onto the targeted device, or you can do a all over, which was done in the previous generations, where you don't target, rather you make a beam which is omnipresent all over the antenna, but that is where the power is wasted. So why I brought that was power. So you have to reduce the power to 1/10, and this is where the beam formation of antenna is very important, and thereby you can reduce the power requirement, hungry power requirement at the base station. At the same time, you got power requirement on the device side, which is battery loss. If you let the network process more than the device, then in that case you can conserve your battery, and so therefore network managed is better than the device managed as far as power is concerned. But some of the things you can compute, because these days the devices are themselves so powerful that a lot of things can be calculated, but your power is the issue. So how to preserve the power is on the device side of it. Then you got availabilities. Of course, every equipment which is business critical or mission critical needs to be available. And for the radio equipment in the telco space, they require a 5 nines or 99.999% available, which is around 5 minutes a year, which is key. And in the cloud, you can do usually with a 4 nines, because you assume that it will break, and therefore the cloud's approach has now been coming to uh, uh, telco cloud, which is cloud native way of doing. Here you don't care, you assume that it will fail, and therefore how do you recover, how do you manage the state, keep the state apart from the stateless, and then put the key value pairs, and put the in memory. There are many ways to do that. That's what is being done. Then coming to the W, we have got 100 megahertz to 1 gigahertz, and I should point you to the equation here. C equal to B log 2, 1 plus S by N, the signal to noise ratio. So uh, the capacity was predicted to be B log 2, L by Nyquist, where L were the levels, but actual capacity limiting, bandwidth limited capacity is this formula. If your signal to noise ratio, example, I can tell you, like example, in the voice case. So you got 30 hertz to 3300 hertz. That's what we transmit for a voice. So if that is difference is around band pass, that is band is around 3000 hertz. So if you do a 3000 hertz, and for that band, and if your noise to ratio is a 1000 to 1, that is uh, that means signal to noise is 30 dB. Then you, in that case, 1 to 1000, so basically what it means is, if you are able to uh, sense the signal on your device, which is nothing but a receiver device, not the transmitter device, then you should be able to uh, get that to provide the value. And you can see it comes out to 36,840 or something as kilohertz. So that is why in the earlier stages, when we had voice modems, they used to limit it to 38.64 or something kilo. So that's what the capacity of the channel is limited by the um, bandwidth that is available. That is why when you talk about bandwidth of wideband, like 5G being 100 megahertz with a carrier, of course, carrier is different. So FC, you pointed here, FC is the carrier, because it's like if you want to go fast, then you take a car and you sit in the car and you drive. Same way, if you want to reach fast somewhere, you have to use the carrier and the so on the carrier, the other waveforms it get modulated. Whichever modulation, whether you use PSK, ASK, QSK, QPSK, usually quadrature phase QPSK, 8 PSK, 64 PSK. Those are the types of phase shifting key modulation we are done in the 5G, and that's being able to maximize the what you call the levels, and at the same time maximize the signal to noise, the capacity. So as long as you have the capacity and the levels that you can transmit through it, it's good one. And this is valid for even for uh, quantum uh, computing in the terms of qubits. So you need entanglement, and also would like some of the faculty members to look into that, and maybe you can do some research work and uh, contribute, because it's a fundamental research. So there is a scope for fundamental research in those areas. So maybe look back at why Nyquist and why not Shannon, or why Shannon, why Nyquist, why not me? Come up with something which we can probably exploit in the 6G era. It's already there, but you need to still make it practical. So those are the things. So this is about the characteristics of 5G described. Now look at the roadmap of the standard bodies 3GPP, the third generation. It has third generation, has come to now fifth generation, but still the name sticks to it as 3GPP. So what we have is in 2020, what happened? The release, usually it takes 5 to 10 years to get really all described. So every 10 years there has been a new change. So 4G started in 10, ended almost in 20 now. 5G is starting in 20 and it will end in 30. Then we'll have to do 6G. So the standards keeps evolving, and deployments keep evolving, and sometimes standard goes ahead, sometimes uh, the deployment goes ahead. But open source has really accelerated the deployment, faster than the standards, and standards sometimes need to evolve. And standards are good for the hardware side of it. Software side of it, anyway, you can adopt. So that is a little bit still okay. Software can go ahead, no problem. So you can see here the release 16. So these all releases started in 1998 or 99, I believe, and still there are 16 releases, but multiple releases cover one generation. So here you got release 16, 17. We started with 15 was the end of 4G, and 16 started with the what a 5G. 16 stage 1, 2, 3. Then you got now 16 is frozen. 17 has also coming to the closure. You can see release 13 is, as you see here, it's here, and then 18 will start soon. So you are seeing that RAN. Uh, there are many committees in this. One of them being RAN, and for the radio access network, that's what we use. All the standards they define, and there are plenty of documents to go through. And in this case, whatever they define, there are multiple standards, like ITU comes up with something, and then HC follows with something, and then IEEE follows with, each one has their own forte area of expertise. And so there's ORAN is another one. So you got Open RAN, that is. And so you got many standards, and mean all standards generally try to accommodate each other. Initially they are unsure, fight with each other, but at the end of it they come to conclusion what they can do, and each one provides their, ultimately align with the mainstream, and the world goes on. And we see the standards including many technical specification, many white papers, many standards. So you got plenty of standards. In this case, we are focusing on 3GPP, RAN 16. So that dynamic spectrum usage is one of them. Like, because you can have a carrier aggregation, and then you can use dynamically. The resources are generally 15 kilohertz, 30 kilohertz. So your resource units are defined at a very granular level within the reference signal. And from reference signal, when a UE connects, it sends the SIB. SIB is nothing but session information. There are SIB 1, 2, 3, 16, 20. I don't know how many are there, but essentially each one of them uh, interacts with the metadata associated and provides the connectivity, all the information. That is, it's a negotiation between the provider and the device. If you are in band 5, am I on the band 5? Can I lock to particular frequency which you can allow me? And then once they allocated the resources in that particular band, within that channel, within that session you are provided. And since it is a multi-user, statistical multiplexing is there. So it's a lot of combination, time division, frequency division, space division, all the fast Fourier transform, IFT, and discrete Fourier transform, all these are applied. So it's a highly technical uh, deployment of the signaling, as well as the bearer, as well as the channel management. And that is why the channel is key, and the capacity is based on the channel that you get. And how you acquire the channel is all, these are the standards will describe all those. What are the stacks? What are the flows, and how would a flow go, and how you establish the pipeline to connect, and how you not only register, you what do you call use create the packet data units, PDUs, and then you complete your streaming through the streaming or whatever data transfer, upload, download, uplink, downlink, and then once you're finished, then you quit the channel so that the others can use. So admission control. There are plenty of things which are there in this, and our goal is to make sure that we are reaching our target technically using this. So somebody in the standards will be able to follow this. And does this standard, is it like every country has a different standard? No, but radio spectrum is different, usage is different, so you have to adopt to some band, some countries. And not only that, when you create a cellular network, you have to have nearest cell to each other, either one cell or two cell away, uh, no interference. So you have to choose frequencies in such a way that they are not overlapping. So there are ways to do that. So so radio management is a big thing, and one needs to know properly what frequency we are dealing with, how we are making the cells, and how we are using them. So now I'll come back to the radio spectrum as a whole, because that's everything is spectrum. You know, the whole cost for the providers, if it is a licensed spectrum, is very expensive, and they invest by looking at where they find the best value for their customers as well as for themselves. So you can see here 2.456 gigahertz. Sub 6 gigahertz is the one which is mostly allocated for and most useful, because they are well tested, well reliable, and people know the characteristics, and both for indoor and outdoor. And these are the ones. In this case, you have seen that what this is pointing out, this is from Qualcomm. What they are pointing out is 1200 megahertz of uh, whatever the 5G spectrum, and 6E for both of them is available, and that's made available by the uh, FCC here in US, and that's available in certain bands. So what are those bands they have described? And you can see here the characteristics uh, of the 5G new radio units in the United States, where you can go. In fact, they have allocated one in the CBRS, which is uh, what you call unlicensed spectrum, and one can use unlicensed spectrum for 5G, which is new. Whereas in India, if you look at it, and power I had shown you, here is the source is Huawei. They have shown that they have 11.577 watt usage in the BBU. BBU is nothing, baseband unit. Baseband means when you remove all the carrier and you just do at the particular, instead of using FC becomes zero, then what happens? Then you got, that is the baseband. So basically it is a band pass or a low pass filter if you apply on that, and that is you get the zero to certain frequency. So that is baseband. So baseband is, you always convert whenever you want to work in radio, you will have intermediate frequency, baseband frequency, and you will have carrier frequency. So different frequencies you translate so that your work becomes simpler. The baseband is the easiest one, because your devices should be able to support the changes in the variations in the frequency, especially semiconductor devices. So that is why you come to the baseband and work on the baseband. So baseband, at the baseband BBU unit, they can see they require for 5G around uh, this many kilowatt, and you can see how power hungry it is. So therefore, we have to reduce the power. That's what I was mentioning. Now coming back to this diagram again, India's 5G trial only began few weeks back. Okay, this is 1 week when I am saying it's not 1 week. Actually, June first week. So we are in the July now. So what it means is that, or around a month, you can say. So in a 1 month, what they have done, at least to the knowledge we have now, N78 band is what is chosen. Sub 6 band it is, and nobody actually bid for the millimeter wave. Of course, government of India feels that somebody could have, but it's economics, stupid economics. So we have to leave it to that. And in the 3.3 to 3.8 gigahertz band is where we have picked our N78. N78 is also used by some of the European countries, and the incumbents like Nokia, others have devices in that. So is Japan using it. So you got quite a bit of usage worldwide, and it's possible to get devices easily. It's a question of band, which band it is, and our band, say in India, are different from the bands in other places. So we will have to make sure that we adopt to those. And this is where the trials are being done. So the trials, the two parties that have come to trial are obviously the two biggies. One is the Reliance Jio, other is the Bharti Airtel. So Reliance Jio has focused on its trial in the what you call its own um, players using uh, the ecosystem they have built. And for them, the software is Redisys. Redisys is they bought for 160 million a couple of years back. They've been integrating them with their software into the BBUs and VBBUs and the Cloud RAN or what we call ORAN areas using Qualcomm and Samsung. So that's one party to the trial. The other party obviously is the Bharti Airtel, which has been working with uh, what you call now they have engaged Tata's. So Tata is part of the software stack, whereas Bharti Airtel has its own implementation. And since Bharti Airtel is more wider global in the sense that they have African footprint, so they do have software from different places. But these two are the major players, and they are trying to implement the N78 band, whatever that band is, devices, because devices have category like narrow band. So you got narrow band transmission for IoT, NB-IoT it is called. So for the narrow band, there is a category of devices. So devices are categorized, and those devices use the band. So one of those 5G category devices with the N78 sub 6 3.3, that is the one used for trial. And on the radio, that is NG-RAN side of it, there are other providers also. In this case, you can see that there are many device players in this. Because end to end, you require not only the user equipment device, you need the in between over there with the radio tower with the antennas. Then from antennas, you need from cell tower or macro cell or whatever your cells are. From there, you need the backhaul. Either if it is in a remote place, you may have a microwave backhaul, or you may have a fiber backhaul. If it is fiber backhaul, then you have to do the CPRI, that is common public radio interface. And CPRIs are very expensive because as the volume grows, then so you have to convert to Ethernet. That means if you have a traffic which is coming in the signaling through the uh, optics, you have to convert them into radio or say electrical. So optical to electrical. So you may have a ROADM, or you may have some other devices which allow that to be transported to. Uh, so one is at the layer, then you have to frame and deframe based on how you are converting and what you are converting. So there is a whole slew of. If you look above the transport layer, you don't see much. You think everything is cool, but when you go below the transport layer, you have to deal with all the physicalities of the media and the associated Ethernet and the synchronization. So those are the aspects, but all these are technical, and once you have what you call the determination that you want to do it and you have the knowledge to do it, then the question is effort. And so at this time for 5G, it is the effort stage, third stage, I would say, on the Indian side of the by the providers and all the combination of thereof. And some of the optical players, I like Tejas for optical devices, and so is SmartLink, so is Sterling. These are on the cable provider side, and they have got optical equipment and others. Then you have got the equipment providers like ITI, which is a good old telephone, plain old telephones player, but they have been roped in because MTNL is there, and Make in India has brought them in, and maybe some of the players like Geo might leverage them. That's a good sign. So they can be the manufacturing players in this. So you have Himachal Futuristic Communication Limited. So there are many equipment vendors, there are cable providers, then there are the service providers, as I mentioned, plus the three major like Reliance Jio, Bharti Airtel, and Vodafone India, three. And the MTNL is the one player which is also included in the 5G, especially related to ITI, as I mentioned. Then cell tower players are like Indus Tower, Bharti Airtel, and Vodafone PLC have some stake in that. They are doing, and same way you got the 5G mobile devices from Airtel, Jio, Nokia, Sony, several of the Chinese players, I would put it, depending on what they bring to table. They bring N78, yes, welcome. So you will find a lot of this. So benefits are anticipated, and that's the reason all these players are interested in it. They will get it if they are able to support and make in India effort, which is what they are doing. Welcome to the world of competition, and that's good. Speaks well, as was done by the NTT and the NECs and along with the Rakuten. So there is a synergy between the Japanese, Indians, and all of them are either together or even in competition and collaboration, both of them, with the European and Chinese and the US carrier and the equipment providers. So that is the story of India at this stage. They are in the another 6 months down the line. We'll have much better idea who has really better. But there are so many regions and so many markets that one may be better at one place, the other may prove to be better. It all depends on the technology they are using. So coming back to now, a little bit more on technology before I close it. So you know that as we said, 3GPP standards are there, good. That's good. But then we need radio standards also. So on the radio standard, we have got something called ORAN, and this has evolved from. It was called. A lot of players have put their efforts in each of the areas. It started with Cisco in some CRAN, and then Cloud RAN, and then somebody did CRAN, and then other players came, and finally it was all merged into one effort called ORAN. So ORAN covers the spectrum end to end, not just focused on only one. So you got different interfaces for different, one for the uh, O2 interface for the cloud, and O1, which is the real interface for service management and orchestration framework. See, we previously spoke only about orchestration. Orchestration is good as long as you are orchestrating your platform devices and all that. But when it comes to service management, you have to go beyond the orchestration. So therefore, in this case, for ORAN, you find service management and orchestration as big pieces, and interfaces being the O1 for the ORAN network functions, because you still just having system doesn't mean anything unless the network functions are handled, because network functions are the boxes which we normally have VNFs, and for the firewall, for the load balancer, for the ingress controller, for the egress, and for the service proxy, service chaining. So there are plenty of network functions which we need to be supported, and that's where the ORAN network function comes in. And ORAN is specific to RAN. It could also be some of the things from the cloud can be adopted, and that's what it is. It's these days everything is cloud native. So even ORAN has a O cloud, and that's the beginning of it. And if you talk about O cloud, then we have to look at what are the physical infrastructure relevant to it. So you got physical infrastructure in terms of devices. You got the near what do you call radio transport, which is for the near real time for the radio intelligent controller. And then similarly, you got the cups, we call it, that is separation of the control and user plane. And here the CU stands for central unit. So you have got OCU, and then CUDU is distributed unit is at the edge, and central unit is at the central place. So DU talks to the CU, and then when you DU talks to the CU, you mention, then the question is, what is it? Is it control signal? Is it user signal? Therefore, you will always have DU, Open RAN, CU user plane, Open RAN, CU control plane. And so all these signalings and supports and associated software components, such as operating system, virtual machine monitor, the container runtime, and over and above it, the actual functions like BBUs and virtual BBUs or container-based BBUs, microservice-based BBUs for the transforms. usually frequency, time division transforms, and the stacks associated. All those are required. So how do you put together all of these is the issue. So the most important piece you have to note here is next generation core needs to tie to the new generation radio. So new radio RAN connects to the next generation through the interface here you can see. So there are interfaces you can see. These are three, red one here, 3GPP defined interface, it is NG interface. And same way ORAN is defined by the ORAN body. So these are standard bodies and interfaces out of scope of ORAN. So some of the interfaces are out of scope, they are not defining it, but those are which neither 3GPP nor have defined, like some of them at this time, but eventually they are following one or the other and they come up. So what I am trying to express here is the overall there is an intention to have all interfaces defined as we go, because you need the minimum viable first, and then once you do the MVP, then you go on to add as you need basis and then define new interfaces. So you can see the split here clearly: NG RAN, next generation RAN versus the 5G core. So when we spoke in the morning, it was about the Magnum 5G core, which is the EPC, the evolved packet core, and EPC for the 5G, which is AMF, UPF, and SMF to manage the session. And these are the you can see this is where we said overall 5G NR. When we talk about new radio, new radio is the GNB, but then old radio needs some modification to support the new radio. Therefore it is not just ENB, it is a next generation ENB. So you have got the XN interface between them, and so on and so forth. There are N1, N2, N3, N4, N5. Various interfaces are named here. The naming is not there, but they are named already. And then what characteristics are already defined by the HC. So it's a matter of deploying, and standards evolve. And here is one more piece which gives you more details, that is at the higher level. Sorry. And this is at the detail layer. But all in all, you can see here the black lines are the 3GPP interfaces to connect the non-real time to the near real time, which is in the real time NIC, which is a RIC, which is the radio intelligent controller, and connecting the ENB, which is the open ENB, or the ORAN defined ENB, which is nothing but same as our ENB, and that's connecting through the E2 interface. And the E2 interface F1, E1 you can see here. So these are similarly, diagrams are similar but in a different way. This is easy to understand. That is a little bit difficult because it has got so many detail. But at the bottom of it, you have got the RU, radio unit, distributed unit. So DU talks to RU, and the DU talks to the CU, central unit. So central unit, distributed unit, sorry, and the cloud. And then once you have that units, then you go into the stacks, and here you got the RLC, radio link controller, MAC, phi layer. So this is the lower layer. Phi low is here, phi high is there. So the split between the phi low and the phi high is the key piece, because that is where the remote radio unit is there. How do you connect a radio unit to the remote radio unit? Whether you do MIMO, how many MIMO? So these are the F2C control plane and F2 user plane. That is key for the radio side of it. Once you bring in from radio, you get into the DU, which is here you can see. Then you talk about the distributed unit. How many distributed units should be connected to one central unit? Whether you have one or you have many, and how many you should aggregate. Those are the issues which are challenges in the field. And then how do you scale it? So not only you distribute, you also split, and then you scale at the central unit. Everything comes together, and then it talks to the G node B. So what here it means is that here you go to the control AMF and UPF, which is nothing but how do you connect using the access management function. Once you connect, how do you manage the session so that the user plane function can connect to these the CUs and the DUs of this world, and do the pipelining of the packet, or forwarding of the packet. And that's what is the key. So you got all the names. I'll leave you with the names to be, but remember CU, DU, RU. That is the order from the core towards the edge. So once you have the CU, DU, RUs defined, then you can get into the lower level split and go into the front hall and deal with the front hall aspects of the RIC and the and that is the real time and non-real time, or near real time, what you call. Those are the ones you deal with. And this is the overall picture. You got the next generation RAN on the left side, and you got the 5G core on the right side. And these are the stacks associated. Each one has their own functionality. In NAS, like example, network access stratum, that deals with the you saw the federated gateway. That means for the 3GPP access. And then you got the idle mode, and so if you are in idle mode, then if you have to be located, there is a area code which will be determined by the TU tau, they call it. So the tracking area, you will be tracked, and then you'll be paged, and that is the portion which is on the mobility side, coming from the MME, or the um, product which is there in the MNO, or mobile operator space, for the control plane. And same way, user plane function deals with the user plane PDU handling, that is packet data unit, mobility anchoring, and all that. So because you got the IP allocation coming out of this, then session management function is the one where you get the UE IP address allocation and PDU session control. So once it is session management function allocates, then the user plane function start tunneling and channeling the traffic, streaming the traffic as you go. And the NGRAN is the one which is the cell. So you got the cell, and that is the core. And when we talk about the PDUs, user plane PDUs have got a GTPU over UDP. GTPU is a special protocol which is always used by the 3GPP for the radio. You can have a GTPU as well as GTPC. That means either you have a control or user, both protocols are available. Here we are showing only the SCTP being used for the control signaling, because that is more secure. So that is over TLS. And then you got the IP and the data link layer and physical layer. So these are the stacks which are shown. So when you go from transmit to receive, or receive to transmit, uplink to or the downlink, the way it goes is it goes top to bottom or bottom to top. Either way, how you enter. If you enter physical, then you come out at the SCTP level. If you enter at SCTP, then you come out to the physical layer. So transmit receive or actually for control plane signaling as well as for the data plane. Then you got the whole corresponding SDAP. SDAP is one of the PDCP SDAP. So normally in 4G you always have a 5, you have a MAC, you have RLC, you have PDCP, but SDAP is one which is new to be able to adopt for 5G. So service data protocol, that is one. PDCP is nothing but to make it in sequence. So radio link control is the RLC. MAC is your standard everywhere, whether it is Ethernet. Whenever you do Ethernet, you need MAC, and physical is the media. So you will find that UE connects to the G node B via RLC, RRC, radio resource control. So because in the case of radio resource, you need to manage the radio resource. So you have to know, we have to know which lat long you are in. And so radio resource control allows you to provide that radio and the API to associate with what and where you are to track your mobility in the cellular network. And then you have got the NAS signaling, which is to provide the signaling to the access control and all that. So you got all the details of the stack one-to-one for transmit and receive, whether you do UE to GNB or UE to GNB to AMF, or UE to bypass the GNB directly do the NAS. So various signaling mechanisms are here. At this time, I will come to conclusion that standards are there, deployments are there. We have seen now radio is under, at least in India, it is under deployment. And the players, one player I forgot to tell you is RANCore. RANCore is a Reliance Jio's company, which is the main player in the field. Like you had the what do you call, Bharti Airtel had a Indus tower. Similarly, these people have the RANCore, who are the integrators who work with Radisys for software, Samsung and Qualcomm for their devices and all, and whatever they have cooked up the recipe in their own geo they use to build a ORAN. And they have used a small cell with airspan. So that is another collaboration. So a lot of collaboration at the same time, trying to do what can be done, having a knowledge to do it on their own. That's the effort they are doing, and obviously they don't have a hurry because the spectrum already they have got what they need, and so it's a matter of trial and proving. And Geo is using the RAN core network and as well as Radisys software. Radisys is a company which I said it used to have BBU out of Portland. They were bought for 160 million, and they were obviously their software stuff is what was important, and they quit the hardware and they started putting the software what they have. And VBBU is a little bit older technology, but besides virtualization, they moved it to the newer what you call the uh, containerized versions and all that. So this is my speculation, even though I am not insider. All I can tell you is that they have got to do what the standards say, and they may have some variation here and there, but most of them stick to the standards to be able to deliver. Because if they want to sell in different countries, they need to do what others as a standard do, or establish the standard, whichever way. So the technical aspect of Reliance Jio is available, and there is a good articles I have collected here for you to view. I will not get into details of it, but there is one camp which is the Reliance Jio Radisys RAN core team, which is one camp in India. The other camp is obviously the 5G Tata and Bharti Airtel group. They have also provided, Tata is providing the software. So now that they have a software uh, combination, these two are going to be taking off soon. Within 6 months, we will know what trials they have done and what they have achieved, and actually how they are going to deliver. So it's a work in progress at this time. So you will find 5G in India sooner than later, and try to match with the N78 devices. So on the side of how do you do it, whether you do TDD, FDD, and TD-SCMA, and all those protocols are very much fixed because you know that they are doing in 3.3 and 78. Then you can go back and track back and figure out all. The faculty experts who are in the radio communication will, I'm pretty sure, be able to do it. So now I have here use cases for 5G. So Magma 5G core, we saw campus network can be done with it's a 5G system. If you try to build a radio which is 5G core and you use a CBRS or equivalent of that, in this case, we have got the, I think it's called as National Frequency Allocation Table, NFATA. 2018 was already released. 2020 is not there, but most of it's almost there in the papers. It should be anytime due. So if you get uh, the 2020 21, sorry, if you get the 2018, we can still follow. I have been following 2018, and we can really figure out on that what frequencies we can really adopt, exact frequencies, and configure our devices accordingly. The 2021, if it gets released after this 5G trials, then we should be preview to that sooner, because devices are the first one to go into it. They will definitely get in another few, probably weeks or so. And then the second one, private 5G LTE network, unlicensed access. Yeah, this is unlicensed access is important, and this is equivalent of uh, what I was talking about, the private 5G, which I expect um, Prem Gopanan, who is an expert in this 6G and 5G era, and he has been earlier he used to work for Ericsson. Now he's in Cohere, and a very good guy to listen to, and hopefully he will deliver on his slides for us to end the talk to go through. Then fixed wireless access. This is the Airtel 5G radio. This is what was done by Verizon in the US. So FWA, fixed wireless access, is a key use case for system point of view for 5G radio. So two 5G systems and 5G radio. Then the next three are more related to the slicing. So extreme mobile broadband is the key word for 5G for the throughput. So 4K, 8K video content delivery can be done using the EMBB slicing for the carrier to experiment on. Then similarly, you can do a massive machine type communication, either weather or drip irrigation for sensing and actuating on the field for agriculture. That would be a good use case for the narrowband IoT and massive machine type communication. Then industrial IoT, which is more latency sensitive. highest latency scenario. In fact, 1 millisecond is the expectation. That is the one which is very critical. And this is for managing the factory automation, as well as for shop floor management, warehouse and drone management and those kinds of. So 5G URLCC is another use case. So I'll say these three slices if we can cover, and one for the radio, two for the systems, that should be more than enough for most of the use cases. All those fancy use cases we may or may not be utilizing in India. So yes, some of them could be. I'm not denying that. If it is available, why not use it? And if you can use it, and if you can get some use cases which is really saving business money or saving government some money in the defense, welcome. You're welcome to try that. So as a faculty development program, I think we can have a forum discussion on this. And I am actually completing the recording at this time, having finished almost an hour and nearly close to an hour. I will stop here, and this is the end of the session for session 2, and hopefully you can hear this in your uh, forum, and then we can go from there. So at this time I will end the recording. That should